Okay, anybody that happens to be watching this is section or chapter 2, which begins on page 58 of the book. You're going to be hearing my voice for a while and not seeing anything, so just listen. Okay, please pass if you've got them done, please pass those assignments forward, and then over to Rachel again. You have to turn them in to get credit. Make sure your name's on them. When you got that passed up here, turn to page 58 and then listen for a few minutes. If you got one done and not the other, then at least turn the one in you got done. Remember, you got to get that other one in. Like, I will give you the chart back for your own reference. Since you wrote it, that means more to you. But I want to get things written in the grade book first, and then I'll give those back. Okay, everybody got to pass forward? Okay, once you have studied calculus, and hopefully fairly close on the heels of finishing, if you want to read a really entertaining book, this is great. He brings it to life. He makes it less than two-dimensional, more than two-dimensional, brings it to life, talks a lot about its development. It's called The Tour of the Calculus by David Berlinski. Anybody that wants to, I'm promoting this book. Yes, I am. I'm getting no kickbacks for it, but it's an awesome book. And once in a while, I will reference this, but if you actually read it after studying all of the calculus, it has a lot of, it's hilarious. It's very, very funny. It's very poignant. It's also, on occasion, a bit risque. Yeah, I know, people are going, that's terrible. He gets a little bit, yeah, it's a little bit racy at times. Okay, but not all the way through. Okay, so this is the part, that's great. This is the part I want to read to you. It's called the frame of the book. It's just this little blurb right here. It's not the frame of the book, it's the frame of calculus. And it'll have very little meaning to you yet, but we'll read it again once in a while, and we'll start to have some you'll understand what's happening. This is how it goes. The overall structure of calculus is simple. It is. The structure is simple and very short, actually. Very powerful, okay? The subject is defined by a fantastic leading idea. One basic axiom. A calm and profound intellectual invention. A deep property, two crucial definitions, one ancillary definition, one major theorem, and the fundamental theorem of calculus. You might think, geez, that's a lot. It really isn't. I mean, it can be put into one sentence, and a sentence is only 5 lines long in this book. Not that long. The fantastic leading idea is that the real world may be understood in terms of the real numbers. The basic axiom brings the real numbers into existence so that we can talk about it. The calm and profound invention is the mathematical function. We will limit our discussion to functions. The deep property is continuity. The crucial definitions, instantaneous speed, and the area underneath the curve. Strange, weird things. Instantaneous speed and the area underneath the curve. The ancillary definition, a limit. And that's what we will study in this chapter, is the limit. The major theorem, which is the mean value theorem. That's pretty important. The fundamental theorem of calculus is, well, the fundamental theorem of calculus. These are the massive load-bearing walls and buttresses of the subject. Okay, so we're going to start with the limit, and we'll talk about how the limit applies to functions and how we figure them and all kinds of things about them. That whole first chapter is about limits and continuity. And then we will begin a big dive into differentiability. And about the middle of January, we will start talking about integration. Okay, At the beginning of chapter 2 on page 58, this is the type of question we will be able to answer once we're finished with this chapter. It seems pretty reasonable, especially in this area of the geographical. An economic injury level, an EIL, is a measurement of the fewest number of insect pests that will cause economic damage to a crop. It has been estimated that monitoring pest populations and establishing EILs can reduce pesticide use by 30 to 50%. That's significant. That's a lot. Accurate population estimates are crucial for determining EILs. We've got to know how many pests are out there. A population density of one insect pest can be approximated, a particular species can be approximated by this function. D of t is equal to t squared over 90 plus t over 3. Not a very nice one, but that's just a parabola. Just a quadratic. But that's how many pests per plant, where t is the number of days since the initial infestation. Now, here's our question. What is the rate of change in this population? In other words, how quickly is the population growing when the population density is equal to an EIL of 20? In other words, how quickly is it getting worse at that instant when the EIL is 20 pests per plant? And in section 2.4, we can answer questions like that. Pretty useful thing. Calculus is very useful. One more bit of reading before we jump into something. At the top of page 59, I always like the way the author summarizes the chapter way better than I can summarize it. So listen up. The concept of limit is one of the ideas that distinguishes calculus from algebra and trig. In this chapter, we show how to define and calculate limits of function values. The calculation rules are very straightforward, and most of the limits we need can be found by direct substitution, graphical investigation, numerical approximation, which is tables, algebra, or some combination of these. One of the uses of limits is to test functions for continuity, to decide if they're continuous at a particular point. Continuous functions arise frequently in scientific work because they model such an enormous range of natural behavior. And they also have special mathematical properties not otherwise guaranteed. Continuous functions do. Okay, so I want you to notice the title to your book. It's called Calculus, and then it's graphical, numerical, and algebraic. And you need to understand what these words mean in the context of different problems, because we will look at all three of these sometimes in the same problem. Sometimes problems lend themselves best to analysis by graphical investigation or by algebraic investigation, or rarely, but sometimes numerical. Now here's the deal. Graphical, you just put it in your y equals screen, graph it, move the window around, move the cursor around, take a look at certain instances where the division by zero shows up, stuff like that. But you're looking at the picture of it. Algebraic is when you work something out from top to bottom. You get a problem, you work it out, you work it out, finally you get either x equals or the simplest possible thing or whatever. Numerical is something we haven't seen a lot of, but it is the table aspect of your calculator, where you can look up an x and a y set of values, and you can look at the numbers as they compare, as they go along. Numerical is the least used, but can be very powerful in certain circumstances. That's what he was just talking about when he says, the calculation rules are straightforward for limits. They're straightforward. And most limits we need can be found by substitution. That's an easy thing. Graphical investigation. We can do that with the calculator quickly. Numerical approximation. Might want to look at the tables to see that approximation of what things are approaching. And just flat out algebra. Okay, so we're going to be using all of them. All right, here we go. Dive it in. 2.1 is called rates of change and limits. What's another word for rate of change?
Acceleration.
Nope. Rate of change and acceleration is a rate of change per time. It's like feet per second per second. It is itself a rate, but it's a rate per time. Rates of change. Another word for rate of change in math is slope. Slope is a rate of change. Okay. So in the very first one, we're talking about average speed, and they've got that highlighted in yellow on purpose. Right at the outset of calculus, folks, you need to distinguish in your mind, put them in separate places, access them differently, some way or another. Make your brain separate the idea of average speed and instantaneous speed. is you got to read carefully what it is they want. Otherwise, you get the wrong answer because you glossed over the word average. And a lot of times when they mean instantaneous speed, they just leave the word instantaneous off. So it's either speed or average speed. We're talking about average speed for a little while here. A moving body's average speed during an interval time is found by dividing the distance covered by the elapsed, the distance covered by the elapsed time. The unit of measure is length per time unit, like feet per second, or miles per hour, or light years per century. Okay. Kilometers per hour, feet per second, or whatever is the appropriate for the problem at hand. Okay. Before I go on, I want you to get a handle on average speed and what it actually means. That definition cannot be glossed over. You have to be very careful with it and do it just right. So consider, for example, a trip from Rexburg to Idaho Falls, and let's say that it is 30 miles. I'm not going to go with the little nitpicky things. 30 miles. And you head down with your empty trailer. You're going down to pick up something. And you head with your empty trailer at 60 miles an hour. And you load your trailer up and you're not really sure about things and you're not a very good trailer puller, you're just kind of new at it or whatever. And you come back at 30 miles an hour. What is your average speed? It's what everybody thinks. Do you agree? Now that I've said it that way, do you agree with Kyle?
Yeah.
Kyle, thank you for speaking up because that's what everybody thinks out in the world. You guys maybe think that because the average of 60 and 30 is 45, right? That is not your average speed for the trip because you spent more time going 30 than you did going 60. So it contributes more to the average. Now here's the deal, folks. You got to understand what this just said. It said, and you may want to underline it, I don't care if you write your book, do it with a pencil. It says, during a time, the average speed during a time interval is found by dividing the distance covered by the elapsed time. You do not just average speeds. You average total distance divided by total time. So what was the total distance in this scenario? 60 miles. What was the total time? How much time did it take you to get down there? How much time did it take you to get down there?
30 minutes.
30 minutes because you were going twice as fast as you had to go. I mean, it was 60 miles an hour. You only had to go 30 miles. That's half an hour. Does that make sense? How long did it take you to get back? An hour. How long were you on the road? An hour and a half. What's 60 divided by 1.5? 40. Average speed was 40 miles per hour. And it's strictly because it leans towards the leans more towards the 30 than the 60 because you spent more time going 30. It had a greater impact on the average. You follow? Total distance over total time. That's what you got to know. Now, let's talk about distance on a number line because that's one of the things you're going to have to figure today. What is the distance between this and this? 10. Can someone tell me how they figured 10 quickly? I mean, how did you get that so quick without grabbing a calculator or doing something silly? How'd you do it? Anybody? 8 minus -2. That's a way to do it. Did anybody go from 2 to 0, which is 2 units, and then from 0 to 8 and add the 2 together? Yeah, that's what I would have done. However, I also know the definition which was brought up, and that is the absolute value of 8 minus 2, -2, or -2 minus 8. Doesn't matter which one you put first. If you absolute value it, you're going to get 10 either way. So since we subtract them, which one first doesn't matter as long as you absolute value it. It's usually big minus little. That'll give you the positive aspect without the absolute value. But you don't have to do it that way. It's just the difference between the two locations. And like if you had mile markers out on the road and you started at mile marker 248, you ended up at mile 287. What do you do to find the distance? You take 287 minus 243. Yeah? You following me there? Mm-hmm. So to find distance, which is this, in our case, we had to add 2 things together. But that's because we went forward and then, if you will, backward, and that was a negative. It was 30 minus -30. If you talk about vectors going in directions. You know what I'm saying? Over the total time, and total time, you just add them up like we did here. Okay. But to find distance, you subtract the 2 endpoints in either order and take the size of it, ignoring the sign. That'll give you distance. All right, let's take example 1 and see if we can answer what they want us to do, what they want us to find. A rock breaks loose from the top of a tall cliff. What's the average speed during the first 2 seconds of fall? What is the average speed? We're after average speed. And you're going, why does she make such a big deal out of it? Because pretty soon we're going to be finding instantaneous speed, and it's a far different process. Okay, so we got this rock falling off a cliff, and somebody was out there just waiting for the thing to break off with a stopwatch and timed it for 2 seconds. And our objective is to figure out what its average speed was. You need to know about falling objects. The distance that they cover, which we will call y, because when we do a graph, quite often this will be distance and this will be time. And so we're calling this is, it's not d of y, but we're calling it the y. This means distance is equal to 16t squared. And if we're being true to the physics, it's really negative 16t squared because acceleration is a vector and gravity always pulls down. There's your negative. However, for our discussion, we won't be true to the physics. Just 16t squared. And it comes from the fact that the acceleration due to gravity when you're measuring things with feet is 32 feet per second per second. And the formula requires us to cut that in half. If you're taking physics, you'll understand why. But we're not. So we're going to take this on faith. This is the time that has elapsed, and this will tell you the distance that is covered in that amount of time. We wish to do it for the first 2 seconds. What will be the total distance covered in the first 2 seconds?
32. No. 64.
You're sure it's 64? To be true to what we just said about distance, it's actually 64 minus 0, because that's how fast it was going at the moment we hit 2 seconds, and this is how fast it was going when we started the clock. So this is the difference between the distances covered. This is the difference between the initial location and the 2 second location. Like the mile markers. It's just this happens to be 0 in this case. So you're right, it's 64, but it's because we're subtracting 0. If they said, what was the average speed between the first second and the second second, we would need this to be 16. You following? Okay. Divided by, and it said the first 2 seconds. Again, that is the final time minus the initial time. That's average speed. We call it velocity average. Velocity is a vector, and we really should make it negative because the rock is traveling downward, but we're not going to pay attention to that yet. And so the average speed is what? 32 what? Feet per second. That's its average speed. That wasn't hard, right? Final location minus initial location over final time minus initial time. So that if the question had asked, what's the average speed during the first between second 1, when it hit the first second and the second second, that average speed would be 64 minus 16. Because the distance covered at second 2 is when you plug 2 in, that gives you 64. But second 1 gives you 1 squared times 16, you subtract the 2. So it was at 64 feet after 2 seconds, but it was at 16 feet after 1 second. You follow? Over 2 minus 1, because again, we're talking about final time minus initial time. And in that case, we would get 48 divided by 1, which is 48 feet per second. Average speed between the second, when we're going to arrive at the first second and the second second, that little bit of time that elapsed for that fall, its average speed was 48 feet per second. So it's, in a general way, velocity average is equal to, and I'm going to say distance, because I don't have a variable for location. I'm just going to say distance final minus distance initial over time final minus time initial. And a more concise way of saying that is the change in distance or the change in time. And that's Greek for, well, that's delta means the change in. Doesn't this right here, doesn't this look remotely familiar? At least this. What does that look like? It's like a slope. It is a slope. Okay, we'll talk more about that a little bit later, but if you look at this graph where this is distance and this is time, this is the difference in the y's over the difference in the x's. Average speed. Okay, we'll talk a lot more about that later, but that, when we said rate of change, average rate of change, average slope. Rate of change and slope, they're synonyms. Okay, now comes your first experience with calculus, because example 2 says, finding an instantaneous speed. The question asked, and this one's easy for this scenario, but boy, it won't be later. This one's really easy for this one. Find the speed of the rock at the instant t is equal to 2. Anybody know? Please tell. If it had a speedometer on it, what would it read right when the clock reads 2 seconds?
64.
It would read 64. We figured that out, and the only reason it worked out this way, this part right here, is because this was 0. Instantaneous speed is from the initial moment we start the clock, 2 seconds elapse, and it has the distance that it covered. That's how fast it's moving per second at that time. And that may not be really intuitive to you. Maybe it is. But we are going to learn a way to do this when it's not so easy with just these zeros here. The first problem that we did, it's pretty easy to figure the instantaneous rate of change because we started the clock at 0. And I want you to think about this slope thing with me for just a minute. Now, I guess I'm not really ready to go there yet. I will in the next couple of sections, but take a look at what the author does. Let's just study the solution so we don't get any farther ahead of ourselves than necessary. The solution says that if we're going to figure this out, we're going to have to use a slope formula, just like I just talked about. The problem is, there's only one spot in time. There's just the t equals 2 seconds. There's not the t equals 0 and then to 2, or the t equals 1 to 2. There is no elapsed time when it's instantaneous. An instant of time has no time which is elapsed. It's a snapshot in time right now, right? It's very instant. How fast is it going? And we all know that's got to be going something. Well, we can't use a slope formula because we would be taking 2 minus 2. We would take a number that's really close to 2. That would be a good idea. So what I'm saying is we could use the slope formula if we're trying to analyze what's going on at t equals 2, if we let it be, we're going to say for discussion purposes 0, just a little bit after. Like maybe we could find the average speed between when it hits exactly 2 and when it hits 2.1. Because that's not much time. And we could average. We could find the distance at 2. We could find the distance at 2.1 by plugging it into our formula that I just erased, y equals 16t squared. We could find that distance. In other words, we could find y of 2 and y of 2.1, for example. That would be what, 64, and anybody figure that out? $70.5. And these are distances, right? We're trying to find instantaneous velocity. We could think of it as average velocity as long as we don't let too much time elapse. We can't have it be an instant because remember the bottom of your slope formula has t minus t. We can't do 2 minus 2. Everybody knows that leads to nowhere. But we could do this. We could say 70.5 minus 64 over 2.1 minus 2. That'd give us pretty good close. We'd get pretty close, wouldn't it? Okay, what is that? $65, isn't it?
Yep.
Okay, and what did John tell us it would be? So that's pretty close. And it might be good for, I don't know if you're approximating really tightly, but maybe we could do this. Maybe instead of this one, we could go y of 2.01. That's a really tiny time. That's only 100th of a second later. Somebody figure that out for me and tell me the distance.
64.6416.
So if we did that, that would be 64.6416 minus 64 over 2 minus 2.01. And what is that?
64.16.
Will it be 2.01 minus 2?
Yeah, should have been that way.
Okay.
Did the person who just said it is 64.16 do that in your head? You could have. 64, a little bit, minus 64, that's this little bit, divided by 0.01, moves the decimal over to. A lot closer to what John thinks it is, and a lot of you think it is 64, the instantaneous rate of change. You see that we could get closer yet if we put 0.001, that's only 1,000th of a second. The main thing is, though, you can't do 2 here and 2 here. You can get close to 2 on either side of it. We could have done 1.999. That would have then gotten us very close to it as well. I bet it would have been short of 64 a little bit, 63 point something small. Okay? And you can see that the smaller you make this thing and do the calculation for average rate of change, you're getting closer and closer and closer to what it actually is, which is 64. Turn the page. You see the table there in the upper left-hand corner? They did a difference of 1 first, and they got 80. 0.1, we got 65.6 like we got. You go on down there and you figure your average speed, and you keep getting closer to those 80s. That's a pretty gross estimate. 65 isn't great. 64.16, the one we just did, that's pretty close. And it gets even closer yet as you go down, really, really close. It keeps adding a 0 in front of the 16. Until you can see that numerically, I'm talking numerical, I'm talking about a table of values. Numerically, if we keep making that time interval smaller, we can see that it's approaching 64, so we believe it's 64, and it is. Everybody okay on that? See how we need to use the numerical approximation? But you can't do instantaneous stuff because you can't have division by 0. And so we have to come up with a better way, an approximating way, and then see what it's tending towards. And when you're looking at what things are tending towards as you keep following the pattern, you're finding the limit. So this is what we say. I want you to notice that we could summarize this rather than with numbers. We could write it like this. We could say, same function right there. We could say, I'm going to call it f so that it makes a little more sense with what I'm about to write, f of x. We could say that f of x plus some little bit, like 2 plus 0.01. If we find that function value, which is what we did here, and we subtract f of x, which is what we did here, and divide it by x plus h, which is the x location for this, minus the x location for this, we end up with f of x plus h, a little bit more than 2, if you will, minus what happens at 2, divided by h, the difference between these two, which is what we get here, was the 0.01 difference, right? You with me? Mm-hmm. Gives you an approximate value. And what we're going to spend the rest of the section, well, a lot of this chapter, is what we do to find instantaneous velocity, not velocity average, but velocity, is we take the limit as that difference goes to 0. We let it get closer and closer and closer and closer and closer to 0 without letting it arrive. Because if we let it arrive, now we've got division by 0 and all kinds of trouble. So the limit is it's not about h being 0, it's about letting h tend towards 0. Okay? All right. I don't know. Let's see if we do that algebraically. Let's go ahead and do it algebraically. In the way for some of you, I hope you can still see. So I want to take this generalized idea, this idea right here, and I want to apply it to this the way they expect you to do it for when you're practicing. So here's f of x. Equals 16x squared, I'm going to say. And according to this, we can find instantaneous velocity at 2. No, I'm not going to do it that way. We can find velocity by taking the limit as h goes to 0 of f of x plus h minus f of x over h. Do you remember this from the paper we did? And I said it's going to become real important to you. I want to leave the limit alone for a minute. I'll come back to the limit, but I want to simplify this for this function. So that would be, what is f of x plus h applied to this function? I'm trying to find this value right here.
16x squared.
16 times x plus h squared. Isn't it?
Yeah.
It's replacing the x in the function with x plus h. That's the thing in the parentheses. Do you agree? Minus f of x, which is 16x squared, all over h. I'm gonna continue simplifying this. I'm not forgetting about the limit. I'm just working on this for right now. That would be 16 times x squared plus 2xh plus h squared minus 16x squared all over h. I'll just keep track of that h. Moving along here, we 16x squared plus 2xh, plus 32xh, plus 16h squared minus 16x squared all over h, and these add out, and they always will when your function's a polynomial. So what I have is this. I'm going to erase this now so I can save myself a line. I have this over h. And remember, when this is a monomial, you can divide it into each separately. So what I end up with is 32x plus 16h. You agree? Okay. If I take the limit as h goes to 0 of this, I'm bringing the limit back home. I've simplified this mess all the way down to here. Now I'm bringing the limit back. What we're saying is, as h, this guy right here, gets closer and closer and closer and closer and closer to 0, this whole function right here gets closer and closer and closer to 32x. Would you agree? Plug any time value you want in here, and that'll tell you instantaneous rate of change for this falling rock. This is a slope or a speed generator. Put 2 in, you get 64. You want to know how fast the thing is going after 4 seconds? If the cliff is far enough for it to drop 4 seconds, you take 32 times 4. That'll tell you how fast it's going, how fast it's moving at that instant. Yes?
Where did the 16 on the h go?
We're taking the limit as h goes to 0. And as h gets smaller and smaller and smaller and smaller and smaller and smaller and smaller, this goes in closer and closer and closer and closer and closer to 0 until we don't have to consider it anymore.
So the x just kind of, or the 16 kind of disappears then, and we're left with 32x.
Mm-hmm. This goes to 0. It tends to work, and it tends so far, so close to being 0 that it becomes insignificant. Our instantaneous rate of change will be 32 times the amount of, the speed of the rock will be 32 times however much time has elapsed. And that will be instantaneous. And we did it by exploiting the rate of change, the average rate of change formula, but letting the h, the difference between the two, get smaller and smaller and smaller, and we came up with a formula which will generate speeds exactly for any time you want to put in there. It's kind of powerful stuff. You're going, yeah, that's cool, I guess. It'll become more important to you later. Okay, the definition of a limit. I want to read it to you once, and then we are going to set it aside until next spring. And you'll see why as soon as I read it to you. But we do have to do it because the professor that runs the AP or the dual credit program at ISU demands that the final exam have one question having to do with the definition of a limit. And so we will learn it when you're a little more mathematically robust. It'll scare you all off if we do it right now. Listen to it. Assume f is defined in a neighborhood of C, and let C and L be real numbers. The function f has a limit L as x approaches C if, given any positive number epsilon, there is a positive number delta, such that for all x's, the distance between x and c is between 0 and delta means that the distance between the function value and L is less than epsilon. If that's the case, then we write that the limit as x approaches c of f of x is L.
Yeah, I don't.
We will set that aside until it has much more meaning for you. You don't have enough experience to deal with that right now. And they introduced it here because we're studying limits. But the author, even of this book, doesn't give you any exercises having to do with it in this section. He knows he'll scare you all off and that'll be the end of my class. So we're not going to do that. But we'll come back to that definition when you're, like I say, a lot more mathematically robust and able to handle it. Okay, so skip that for now. There's your definition. It's been defined. It's been proven. Mathematicians who study this stuff believe it's true, so you will too because you're going to take it on faith. Okay, the next thing I want you to do, and I think the author should have put this in a box or an example or something because it's kind of important. It's not kind of, it's really important. And it's right down here at the bottom of my book. I have it circled. This thing right here is what we're focusing on, the circled part at the bottom of the page. See it down there at the bottom where it says, let's see if we can find the limit as x approaches 0 of sine x over x equals 1. But this time we're either going to use tables, or if I were you, I would use a graph. So what I want you to do is to graph sine x over x. Make sure your calculator's in radian mode and then leave it there for the rest of this course. Sine x over x, I want you to graph that function because that's what we're limiting is the function, sine x over x. And tell me what you believe the value is when x is 0. Ask your calculator, what's the value of this function when x is 0? And what does it tell you?
No, it doesn't.
It tells you can't find it, right? How come?
Because it's divided by zero error.
Yeah, because
Oh, because you can't divide by zero.
Yeah. If we ask it to find f of 0, we've got division by 0. Even though the sine of 0 is also 0, 0 over 0 is undefined for us for now. Can't find it. And your calculator can't find it either because it calls for division by 0.
Yeah.
So what I want to know is, what is the limit of this function as x approaches 0? And what that means to you, and this is a concept that will develop as you go along through this section. What this means is, what does this value, as I get closer and closer, as x gets closer and closer and closer to 0, what does this function get closer and closer to? So what you could do is, you could ask the calculator in the graphing screen, what is the value of this when x is negative 0.01? Close, right? What's negative point? What is it? Negative 0.01. What that value?
I literally said
It's like it's getting very close to 1.
Yeah, it is getting closer to 1, and you can tell that from the graph, right?
Yeah.
Because it looks like it passes right through the 0.01, but it doesn't. There's a hole in the graph there. This function looks like this. If this is 1, it comes down like this and does some other things over here, and then there's a hole right here. So when we're talking about the concept of a limit, what we're saying is, as you are a little speck or a little bug on this graph, and you move from either side, you move closer and closer and closer to x equals 0. So here you're here, you get that value. Here you're getting that value. Here we're getting this value. Here we're getting this value. As long as we don't arrive there, what is this thing approaching? 1. So even though there is a hole when x is 0, there is no value of the function there. Its limit as it approaches 0 is 1. That's what it's getting closer to. That doesn't mean it has a value of 1 at 0. It has no value at 0. But the limit as we get closer to 0 is 1. Because right here it's really close to 1, and right here it's really close to 1. And the closer we get on either side of it, we get closer and closer and closer to a y value of 1. This has nothing to do with what happens at 0. It has everything to do with what happens to the y's as we get close to 0. They are getting closer to 1. So we have to say the limit is 1. It's not approximately 1, it is 1. Because that's what this is getting closer to as we get closer to 0. Okay? This fact This particular fact is very important for a lot of things we're going to be doing in the next till November. This is an important thing to remember about sine x over x, that its limit is 1 at 0. Its limit at 0 is 1. It's an important thing. Okay? So you might want to put that down on something or remember how to reference this or whatever, but it's a really important fact. It's not very hard to remember, not very hard to memorize, but it's important. Okay, now I want you to look at the top of page 61. We're not going to get close to finish with this section today, so doesn't mean you don't have an assignment. It means you go as far as you can tonight so you don't have so much to do when you finish it. Okay? So, and the only reason I'm staying on this board is because I got to stay on there for Jeff.
Jeff.
Hello, Jeff.
I want you to read the bottom paragraph with me at the bottom of page 60 because it reiterates what I've just told you, and it's really, really important when you talk about limits. It says, figure 2.2 illustrates the fact that, and I have this underlined, the existence of a limit as x approaches c never, ever depends on the function's value at c. We do not care whether it's even defined there, as in this case. We don't care what happens at c. We care about what happens as we get closer to c. What the y values are doing as we get closer to c. The function f has a limit 2 as x approaches 1, even though f is not defined at 1. What function? Did we switch gears? Sorry. Figure, yeah. It's at the top of the next page they're talking about. Sorry. Yeah. That figure, because it starts out figure 2.2, and I glossed right over that. So you're looking at the top of page 61 as I read this. It says, the function f has limit 2 as x approaches 1, even though f is not defined at 1. When x is 1. The function g has limit 2 as x approaches 1, even though g of 1 is not 2. And the function h is only one whose limit is x approaches 1 equals 1. They're talking about the three things side by side. So let's look at those graphs a little closely. I don't like his words. We're going to talk about them one at a time. Take a look at the top of page 61. We have the function x squared minus 1 over x minus 1. Okay, that's the function we're considering. And that function is a line. However, when x is actually 1, we get 1 minus 1, which is 0. And so there's a hole in the graph there. Because when x is 1, there is no function value. But every place else there is. Notice in the second one, they're talking about a new function g, which has a piece of it that's just like that one. But the other piece says that y is going to be 1 when x is 1. That's assigning a value. So this function right here is still not defined when x is 1. But we can assign that value when x is 1 to be whatever we want. They assigned it to be 1. See that dot sitting there at the point 1, 1? We can even assign it to plug the hole. We can say, yeah, it's not defined at 1. And they've got a whole different h there. I'll show you where that comes from in a minute. But we could also make a function like in B part where it's a piecewise function. And we could say, yep, it's not defined when x is 1. But if we let y be 2 there, then we plug the hole. It's called a removable or non-removable discontinuity. We discussed that in Calc. You remember? This is a removable discontinuity because you just jump over the hole and you're back on the graph. It continues on past that. Why is the last one just h of x equals x plus 1? Because if you take this function here and attempt to simplify it, you get x plus 1. And that plugs the hole. However, we began with this. There's still a problem when x equals 1. If you simplify that, it takes care of the problem. I don't like taking care of the problem, so I much prefer to assign a value. That means that you've considered that this x minus 1 causes problems. This x equals 1. Okay, but what I'm trying to tell you is that this function is this line. It is. This function is this line with a slope of 1 that crosses the y-axis at 1. Look at it. All three of those cross the y-axis at 1. And they all slope 1. But this one doesn't have a hole. We lost it. We lost the issue. We lost the thing that was causing us trouble when we canceled that. Still, this was the original function. There's still a problem here. But this fixes it. Okay, I think we've got time to discuss the properties possibly, because once you see one explained, the others fall into line very easily. Properties of limits. If you're considering two functions at the same time, I have no idea what they are. They're just two functions, f and g. If f has a limit at L, this is what I mean. This is what I mean. If I erase this stuff. Don't forget this fact about signs. It's going to become important, especially tomorrow with our discussion. So here's a function, strange function, f. And this is, where are we approaching it? The next approach is C. So here's C right here. Go up here to the graph. Right there is the point on the graph. Over here then is L. That's the y value that this function approaches when x is C. Because there's no hole, there's no problem, there's no nothing. As you approach C, L is approaching, or the graph is approaching, the y values are approaching L. Yeah? So we say, if this is f of x, is some function out there, then the limit as x approaches C of f of x is L. That's what we're saying. That's the notation we use, okay? Got another function, g. The limit as x approaches C of g of x, that's going to equal m. So that means that right here, see that this value over here, that's m, because this is g of x over here. Are you with me? So it's m is what? M is the y value for g at C, and, well, it's the limit. We don't know if there's a whole lot of problem there, but the limit is. And the limit for f, as we approach C, x approaches C, the y values are approaching L. So this is what L and M mean, the places on the y-axis that the function is approaching as we approach it. Got that? Here's the things. These are the properties. We're not going to prove these. These are just facts. The sum rule says if you add f of x and g of x together and get a new function called f plus g, then the limit at C of that new function f plus g will be m plus L. If we add these two functions together, we take each of the y values, add them together, and get this new function, it's going to cross, at C, it's going to have a value of, let's say m was 2 and this was 10, it's going to have a value of 12. At C, the new function, if I were to graph it, f plus g, it would have a limit at L plus M. Same with the difference. Same with the product. Same with the constant multiple. If you multiply one of the functions by a constant, then the new limit at C will be that constant times the old L. Same with quotients, so long as n is not 0. Same with power. At the very top of the page, if you consider just f and you raise f to some power, r over s or whatever, then the limit at C will be L raised to that same power.
So you just square it, or it's just going to be L squared?
Yeah. If you square f of x, then the new limit of as we approach C of f of x squared will be L squared.
Why did they do R over S?
Because they want you to realize the point fractional exponents for it's just fine. This is good. They're just trying to get you to consider all possible things that we put in there for them. It actually works, if you believe it or not, with irrational numbers. That should just say L to the m, where m is any real number. Okay? It doesn't have to be a fraction, or it doesn't have to be a whole number. Anyway, those properties hold like you might expect. Sum, difference, product, constant multiple, quotient, and power. You do something to f, do the same thing to its limit. Before you did that, you got the limit of the new function. I think that's probably a really better spot when you're right in the middle of the concept. You have plenty of information to get started on this assignment. So get done what you can. We'll finish this lecture tomorrow, and then I'll give you the rest of the day to work on. By the way things will go in here, since it feels like we don't have that much to cover. After a lecture, very typically, I will always give you a day after to just work on it in class. But listen, folks, almost exclusively, you will not be able to get one of these assignments done in an hour or 2 hours. Very time-intensive class, okay? So just having tomorrow, a free day to work on it does not mean you won't have homework. It just means you knock it back a bit. and be able to answer or ask questions.
Do we keep the books or do we stack them back?
Nope, keep the books.
That's it for now.